So a quick reminder that a critical point of a function f is any place where f prime equals 0 or f prime is undefined. And you'll recall that we first learned that definition when we wanted to look for extreme values, because we said extreme values, they only occur either at endpoints or at a place where a function sort of turns around. And that can happen because here the function flattens out and I have a horizontal tangent line, an example of f prime equaling 0. That's what happens here too. That's a relative minimum, up here a relative maximum. It could happen at a place where I have a corner as well, in which case f prime would be undefined, but you can still see I have a top of a hill, I have a bottom of a valley. So this is exactly what we're going to use when we go looking for extreme values, relative extreme values in this chapter, in this section, absolute extreme values in the next section. We want to be able to look for places where our graph turns around, because that's really what makes the top of a hill or the bottom of a valley. So we have an important tool in calculus. We call it the first derivative test, because it's a test based on the first derivative. So imagine I know something about the critical values of a function f. If I can put together a sign chart for f prime, so the derivative of f, and I can find out that f prime changes from positive to negative at a certain critical value, then imagine what that would look like, right? If f prime changes from positive to negative, that means f must have changed from increasing to decreasing. What feature do I have there at that place where f prime changes from positive to negative? It's a relative maximum. So if f prime changes sign from positive to negative at some critical value c, then f of x has a relative maximum at x equals c. Remember, an exactly equivalent name for relative maximum is local maximum. So feel free to fill in either one there. Similarly, if f prime changes from negative to positive, that means the slope must have changed, the slope of f must have changed from negative to positive. F must have changed from decreasing to increasing. And what do I have there? I have a relative minimum. And recall that just because a function has a critical value at, for example, c, doesn't mean that there is a top of a hill or a bottom of a valley. It's just the places where the possibilities are. So I can imagine this curve, x cubed. Imagine x cubed. Right there at x equals 0, I have a horizontal tangent, because if f equaled x cubed, f prime is 3x squared, and f prime of 0 equals 0. So I found a place where the derivative equals 0. But just the fact that it's a critical point doesn't make it a relative min or a relative max. The derivative, f prime of x, has to change sign. Notice here this function, x cubed, is always increasing, so f prime must always be positive. Notice 3x squared has no negative output values. So you can't just go looking for critical points and assume they're going to be relative mins or maxes. You have to double check that your derivative, your f prime, actually changes sign there. If you have a critical point c at which f prime does not change sign, either was positive and stays positive or was negative and stays negative, you have no local extreme value at that point. All right, so now I want to practice using the first derivative test. Can I use the first derivative test to find out if this function, y equals x cubed minus 12x minus 5, has any local extrema? So that's tops of hills, bottoms of valleys. There we go. So I'm going to need to find the critical points. To find critical points, I need my derivative to equal 0. So I start by finding the derivative, make 100% certain you find the derivative, and label it as such. So if y prime is 3x squared minus 12, I'm going to set y prime equal to 0 and solve for x. So 3x squared minus 12 equals 0. I have a couple ways to approach this, but I'm going to divide I divided both sides by 3. Now I can factor, and I have two solutions. So y prime equals 0, the derivative equals 0 at the place where x equals 2 or x equals negative 2. Now remember, it's my job to stop and think, are there any x values for which y prime is undefined? Because y prime equals 0 isn't the only place to look for critical points. But if you'll notice, our y prime in this case is in fact polynomial, has no holes in its domain. So there are no x values that make this expression undefined. So now I use, in sort of the same way that I solved quadratic inequalities, I'm going to use this number line to organize my work. There are two x values that make my polynomial equal to 0. And I'm going to test a number from each section to find, notice I'm interested to know about the sign of y prime. I'm going to test a point on each interval. Let's see, I can imagine testing x equals -3. I'm looking here. -3 plus 2 is negative. -3 minus 2 is also negative. A negative times a negative would make that whole section of the number line positive. If I test x equals 0, I'm going to end up with a positive, because 0 plus 2 is positive, times 0 minus 2 would be negative. Negative. That third interval is going to be positive. Again, if you can do this without testing numbers, that's fine. Just make sure you're not letting anything fall through the cracks. All right, so once I have that sign chart completed for y prime, I know that for x values to the left of -2, my outputs are going to be positive. Between -2 and +2, my outputs are negative. And to the right of 2, x equals 2, my outputs are positive. I can apply that first derivative test. Any place that this derivative changes from positive to negative, and look here, this derivative was positive, and right here it changes to negative. So at x equals -2, y has a relative maximum because y prime changes from positive to negative at that x value. I was looking for any relative extrema, so there's also a relative minimum, because look here, in this middle interval I have a derivative y prime that is negative, but right here at x equals 2, what happens? That derivative changes from negative to positive, so y also has a relative minimum at x equals +2, because y prime changes from negative to positive at that value. For that second example, example B, I notice I did not actually label that function, so go ahead and call it y, like you can see I've done here. Oh, I see also that my subtraction signs are missing. This is horrible. Okay, so use the first derivative test to find relative extrema for y equals the quantity, x squared minus 3, times e to the x. So I'm going to look for critical points for y. That's any place where y prime is undefined or y prime is 0. So I start by using the product rule to find this derivative. The derivative of x squared minus 3 times e to the x is the derivative of e to the x times x squared minus 3 plus the derivative of x squared minus 3 times e to the x. So you can see that even though it took me a while to get it out of my mouth, that's the derivative right here. So question number 1, is y prime ever undefined? X squared minus 3 is never undefined, nor is e to the x ever undefined. There are no holes in the domain of our derivative. So I'm just going to check for places where y prime equals 0, and those will be my critical points. All right, so watch what happens. We know the calculus tells us that we need to solve y prime equals 0. So I replaced y prime with 0. Here I am. And I hope the part we did about solving polynomial equations didn't freak you out, because now all of a sudden we've kicked it up a notch. We don't just have a polynomial equation, we have a whole polynomial times an e to the x. We have a couple of them added together. So our only technique for solving an equation that might have more than one solution, an equation where the degree on the variable is more than one, or where we have multiple different kinds of functions, even not polynomial functions, all mixed in there, is to try to factor and use the zero product property. So I've distributed my e to the x here, you can see, and I want to try to factor. So are there anything I have in common here? I have an e to the x as a factor, so you can see I've factored it out here, and I'm going to collect together all the rest of my factors. So all the rest of my, whatever was left over, into one other factor. So I have this e to the x times the quantity x squared plus 2x minus 3. Now x squared plus 2x minus 3 factors, and I get two solutions. You can see here that's supposed to be a negative 3. Somehow my subtractions or negatives didn't show up at all on this page. Notice here, when I get here, how do I solve this equation? If two or more factors multiply together to give a product of 0, then one of the factors must have been 0. So in my head, I'm sorry I did it in my head. I didn't have to do it in my head. I can write it out for you here. I'm asking myself here, could x plus 3 equal 0? Yes, if x equals negative 3. Could x minus 1 equal 0? Yes, if x equals 1. Could e to the x ever equal 0? No. So that's why I want you to have that function book from the beginning of the year. Is there any value of x so that I could raise e to that exponent and I would get 0 out as the answer? No. So another way to remember it is y equals 0 is a horizontal asymptote. So there's no y equals 0 on the e to the x function. This problem, a problem like this, is the most important reason to know how to solve that equation e to the x equals 0. By which I mean it has no solution. So you have to know that it has no solution. So I have two solutions, which means I have two critical points. So I'm going to mark them on the number line. All right, so I have two zeros, two roots, two solutions to the equation y prime equals 0, two critical points, two numbers I've marked on my number line. Those two numbers on the number line separate the number line into three separate sections. I'm going to test a point from each interval. You might recall that e to the x, no matter what x value you choose, that result is going to be positive. So I wouldn't ever want you to just cross this guy out like I'm about to do. But for what we're about to do, to try to decide at what values y prime is positive and at what values it's negative, multiplying by e to the x is like always multiplying by a positive number. It's not going to change the sign of your result. So we end up with something equivalent, an equivalent sign chart to as if we just had x plus 3 times x minus 1. So you can imagine multiplying that out. It's going to be a parabola with a positive leading coefficient. This interval will be positive, negative, positive. But if you don't believe me, you should totally check that for yourself. And notice that it was only legit to cross that guy out because we knew it was positive. If it were negative, that would totally change. It would change the order of these signs, and we want to make sure we didn't just cross it out. Okay, so now I can make my conclusion, right? I can tell where my derivative, y prime, changes from positive to negative, and where it changes from negative to positive. So here's my conclusion. Y is a relative minimum at x equals negative 3 because y prime changes sign from positive to negative there. And y is a relative minimum at x equals positive 1 because y prime changes sign from negative to positive there.